Good morning, Panthers. It's Dr. Augustine, and I hope you all are doing well today. I am going to talk about acid-base titrations, and this is section 17.4 intro. It is arguably one of the more, confusing, maybe too strong a words, but one of the trickier sections in terms of the calculations, because you got a bunch of things you got to be aware of. So I'm actually going to break this section, believe it or not, one section into 4 videos. And hopefully by breaking into 4 videos, it will make more sense how to attack these problems. Once you have a general strategy for attacking these problems, it isn't really that bad to do them. But if you don't go into it with a systematic way, it gets a little bit confusing. So let's start by just reminding ourselves what an acid-base reaction is. You've actually all done this in lab. Burette is sort of typically used. Remember, it's graduated, it's got markings on it, how much you have. You have some amount of initial, you could do either acid or base. In this picture, we have an acid in the solution that we're titrating, and then we have some amount of base here in the burette. The picture here, these little red guys are OH minus ions, and then they react with the H pluses that are in here to form water. So our generic reaction is H plus plus OH minus, I should put little aqueous next to this, yields H2O. That's the net ionic equation for a generic reaction. We did this last semester. You've talked about this a whole bunch of times. And so that's the generic reaction. If you want to use the nomenclature we've been using in Gen Chem 2, that H plus, whenever you see the H plus, it really means H3O plus, aqueous plus OH minus, aqueous yields 2 H2Os. Okay, and that's just called a neutralization reaction. You've done a bunch of these before. Another thing you might want to note is I'm only drawing this arrow in one direction. This is a very, very favorable reaction in terms of K. The K lies heavily on this side of the equation. So H3O plus OH minus yields water molecules. It's not an equilibrium reaction per se. Okay, and then you've done this experiment before. You put some indicator in here. The one we typically use is called phenolphthalein. We're going to talk about that in one of the later videos. And as you add OH minus, it starts turning pink. And the reason is because the pink color occurs at a higher pH. So once you hit the magic spot, and I would actually not call this picture the equivalence point, that's beyond the equivalence point, then you can say, all right, I've stopped the reaction. So let's put a few names on this as well. So this indicator change we call actually the endpoint. So this is a little distinction that we need to make. So the endpoint is when an indicator changes color. The equivalence point is when the number of moles of acids, the number of moles of H3O plus, is equal to the number of moles of OH minus. Okay, so the equivalence point is when the mole ratio has exactly been reached and the chemical reaction is now equivalent to one another. So there's a little bit of distinction. You want to try to choose the indicator in such a way that the equivalence point and the endpoint are actually the same thing or close to the same thing, but we'll find out in one of the later videos, they're never exactly the same point, and there's some sort of little details related to why that is. All right, so just keep that in mind, a slight difference between the two things. We're going to try to pick an endpoint that's the same as the equivalence point, but the equivalence point is really where the number of moles are equal to each other according to the stoichiometric ratio. All right, so the next key distinction that we need to make is we need to determine whether our reactants are strong acids, I should say strong acid base, or weak acid base. Because we have to handle the reactions a little bit differently depending on whether they're strong acids or weak acids. And that's going to be the subject of the next 2 videos, determining or breaking down whether you have a strong acid, strong base reaction or a weak acid, strong base reaction, or vice versa. Okay, and so let me show you I'm going to give you a preview of what's coming so you kind of know what you're shooting for. So we can make a plot of volume of base added. Now this is NaOH. You should be able to identify that NaOH is a strong base. Volume of base added versus pH. And this particular case is the strong acid, strong base case. And what we can make is what's called a titration curve. So we plot the pH on the y-axis. We plot the volume of base added in this case on the x-axis. This could be acid added depending on the situation. And we get a graph that looks something like this, kind of an S-shaped curve, very steep right around here. And the equivalence point is exactly at the middle. And if you look really carefully, it's exactly at a pH of 7. Remember, the pH of 7 is a neutral solution. So for the case of a strong acid and a strong base, we're going to get a pH curve that looks something like this and with an equivalence point equal to 7. Now, the next video is going to deal specifically with strong acids and strong bases. We're going to calculate a couple of these points along this curve. So you can do it experimentally. I mean, you can have a pH meter or something and measure the pH as you add volume of base and you trace out this curve, or you can actually do it theoretically. You can calculate the volumes based on the number of moles. You can calculate what this pH curve is. That's the subject of the next video. The other case is a weak acid and a strong base. We could also flip this around to say a weak base and a strong acid, but it's the same general idea. The curve is reversed, but the idea of the curve is the same. So once again, we have pH on the y-axis. We have volume of sodium hydroxide added on the x-axis. And you see it's a little bit different. You notice this curve is kind of flat all the way along. I mean, it's kind of linear all the way along and then curves up right near the equivalence point. It starts curving up and it shoots up really fast. Whereas this one has an initial kind of jump and then it's flat for a region here and then it increases again and then it goes up and flattens out again. So I'm going to say this now. I'm going to say it several more times as I go through these videos. But there's actually 4 distinct regions in this curve. And when we do calculations, we need to consider these 4 regions. So here's region 1, and this is no base added. Or more generically, no titrant added. Okay, and that actually is a chapter 16 calculation. In the third video, I'm going to do a specific example of this, the whole weak acid, strong base titration curve. And we'll talk about this first point here. You did this in chapter 16. It's just take the weak acid, you know the concentration, and calculate what the pH is. That's a problem you did in chapter 16. So that's the first step of this titration curve. But there's actually 3 more regions that we need to consider. We need to consider the region once I add a little bit of acid all the way up to the equivalence point and just slightly below the equivalence point. And that's actually the buffer region. And in order to do the calculations of the pH, the theoretical calculations of the pH in this region, we need the Henderson-Hasselbalch equation. I'm going to call this just HH. Okay, so in other words, everything from the very initial spot all the way up to and just slightly below the equivalence point, we're going to use the Henderson-Hasselbalch equation. It's basically a buffer calculation. At the equivalence point, it's an exact calculation, and we're going to just use stoichiometry at the equivalence point. So the equivalence point is then a stoichiometry calculation. And then once we get past the equivalence point, so from the first little bit past there, this is an excess reagent problem. So that excess reagent in this particular case is OH minus. So we're going to use the concentration of OH minus to find the POH, and then from the POH, we can find the pH. Okay, so that's the subject of video 3. That's probably the most involved of all of them, but I want you to recognize the curves are a little different. The other thing I want you to recognize, and I didn't point this out a second ago, but notice where the equivalence point is. The equivalence point is actually above a pH of 7. Now, look, you're used to thinking of, well, if I mix an acid and a base together, I neutralize the solution. I make a pH of 7. That's only true for a strong acid and a strong base. when we mix an acid and a base together, but one of them is a weak acid and one of them is a strong base, we end up with a pH above 7. That's because we have the weak conjugate base left in solution. And again, video 3 is going to be the subject of this. We'll talk more about this. But that's another point I want you to make. Okay, and then let me just point out, just so you kind of know where we're heading here. Similar curves would be pH versus volume acid. This would be if we had a strong base being titrated by a strong acid. And the pH curve is going to look something like this. It's basically this. It's basically the exact same curve as that, only it's inverted. And this would be volume of acid now along the x-axis, and pH is still on the y-axis. I don't have it quite drawn. It's goes down a little bit, goes really steep, and then continues going down a little bit. Okay, so that would be a strong base being titrated by a strong acid. You basically get the exact opposite. And if we had a weak base being titrated by a strong acid, we get something like this, kind of a curve, flat, and then goes like that. So it's basically the inverse of this case. So this is a weak base, strong acid calculation. And this one we'd have volume acid along this axis and pH along this axis. Okay, so that's kind of where we're heading. Those are the next couple of videos. Now, before I stop this, I want to make one more point. I'm talking about strong acids and strong bases. You need to know which acids are strong acids and which ones are strong bases. Okay, in order to identify this, so the very first thing you should do when you get a problem related to this, where it says something like, calculate the pH of such and such a reaction, the very first thing you should be doing is you should be saying to yourself, are these species strong acids or strong bases, or weak acids and weak bases? Because that's going to determine how you approach these problems. If they're strong acids or bases, it's going to be one of these two curves. If they're weak acids being titrated with a strong base, or vice versa, it's going to be one of the second two that I showed you. And if it's a weak acid and a weak base, it's going to be a different type one that's actually similar to these. Okay? So if you don't know your strong acids and strong bases, make sure you know them. There's a list of about, I think there's about 9 strong acids and strong bases that you should know, which you would have learned in Gen Chem 1. All right, it's a good place to stop this video.